This video covers Lesson 33 from Spectrum Chemistry titled The Double Switch. It discusses the double displacement reaction, also known as the double replacement reaction. Here's the general form. Here we have a compound containing substances A plus a compound containing substances C and D. These are both reactants. The arrow then shows the reaction continuing to produce two new compounds in which the original reactants exchanged partners. So we have products AD and BC. The reactants are both ionic compounds in aqueous solution. Remember what aqueous solution is. It involves water or another polar covalent liquid as the solvent being the liquid a substance is dissolved into. And remember what polar covalent means, a molecule in which electrons are shared unequally, so it contains partial positive and negative charges. And remember what an ionic compound is. An ionic compound can be composed of a metal, which is sometimes hydrogen and a nonmetal, or a metal and a polyatomic ion, or even two polyatomic ions. Those ions have an opposite charge, and as they have exchanged electrons to develop those opposite charges, they've also become attracted to each other and connected to form a compound. When you take that ionic compound and dissolve it in water, because the bonds are the attraction of opposite charges, those compounds separate in water into their individual ions. Ions, remember, are atoms with a charge. They do this because they're attracted again to the polar attraction of the water molecule with its fractional charges. In a double displacement reaction, the ions from those two different ionic compounds are floating in solution, able to interact with each other as well as those water molecules. For a double displacement to be successful, a product must be formed, which comes out of solution. There are three possible product combinations to look for. Products which will result in a successful double displacement reaction would be an exchange between the two original reactants to produce both a water and a salt, or one of the products being a gas or an unstable compound that then breaks down into a gas and water, or a solid which is insoluble in water, that means it can't be dissolved in water, and therefore it falls out of solution as a precipitate. A precipitate is just what we call a solid that doesn't dissolve in water that comes out of solution. You may wonder exactly what is meant by gas or an unstable compound that breaks down into water and a gas. These are some common gases to look for as products in a successful double displacement reaction. Notice the H2, Cl2, O2, N2. You should recognize those as homonuclear diatomic molecules. There are 8, remember. They always exist in nature, bonded with an atom of the same element. And then we have the unstable compounds and their products. These are 3 common unstable compounds. The second one, for example, H2CO3, that's called carbonic acid. You find it in things like soda pop. It breaks down to form water in liquid form and carbon dioxide gas, either of which is a necessary product for a successful double displacement reaction. The third item to look for would be a solid which is insoluble in water and falls out of solution as a precipitate. In your textbook on page 129, Table 1, titled Solubilities of Ionic Compounds in Water, provides some information to help us with this. Here's a partial explanation of how to read that table. Not a perfect scan, but again, you can look at it on page 129 of your text. Since ionic compounds break down into their charged parts, this solution, remember, contains anions, the negatively charged parts, and cations, the positively charged parts. This table looks at a product by breaking it down into its potential anions and whether or not they combine with particular cations to be soluble or insoluble. If the resulting product includes a cation from the column in the table labeled insoluble, that compound combination between the anion listed on the left and the insoluble item listed on the right will form a solid and fall out of the solution as a precipitate. Let's look at one of the possible anions and its possible product combinations. According to the table, the anion sulfate, which you know is the polyatomic ion SO4 with a -2 charge, forms a soluble compound with all cations except the ones listed on the left or the right side of the table under insoluble: calcium, strontium, barium, mercury, lead, and silver. So we will end up with compounds calcium sulfate, strontium sulfate, barium sulfate, mercury sulfate, lead sulfate, or silver sulfate. You may find it helpful to rewrite Table 1, listing out the completed compounds that they are explaining to you in the table. Makes it a little easier to analyze the problems that you're going to be doing in the exercises. It's always nice to have a plan when you go in to solve problems like this. So here's a process for predicting whether or not a double displacement reaction would take place. You're going to be given 2 reactants. First, break down each of those reactants. Each is going to be an ionic compound in aqueous solution. Note the charges of each individual ion. Then swap the partners from the 2 compounds to create new compounds and analyze those results. Let's do a quick walkthrough of exercise 1, page 130. The reactants are lead nitrate and potassium hydroxide. Remember, first we break down each reactant, noting the charges of each ion. Okay, normally you'd write this all in one line, but I was going to run out of room. So you see we have lead with a +2 charge, and nitrate with a -1 charge. Remember, of course, the polyatomic ions react as entities, so they don't break apart into, for example, nitrogen and oxygen in the case of nitrate. And then you also have potassium, which has a +1 charge, and the hydroxide ion with a -1 charge. Swap out those partners to create new compounds. So we'll put together the lead and the hydroxide, and the potassium and the nitrate. Once we've put together our new compounds, we need to analyze the results. The table tells us that any time we have a compound composed of nitrate and anything, it's soluble. So that tells us that potassium nitrate will be soluble. Looking at the compound lead hydroxide, we see that the hydroxide is paired with lead. Since lead is not from column 1A and is not strontium, barium, or calcium, as identified in the soluble column in Table 1A, that means that lead hydroxide will precipitate, and this double displacement action will successfully take place. And here we have that balanced reaction.